Great. Hello, everyone. My name is Evan Yu, and that's my baby boy, Aaron. So I'm the author of Vue.js. Previously, I worked at Google Creative Lab and Meteor, and now I'm working full-time on open source project called Vue.js. So how many of you have heard of Vue.js? Wow. A lot of you. Great. So that's my Twitter handle and GitHub handle. Both are really hard to remember, but I believe they are on the website. So today's talk is about front-end performance, more specifically front-end framework performance, because front-end performance in generically, it's a very big topic. So it goes all the way from page loading to client initial render to client hot updates to raw.js performance. But we're going to be mostly focusing on the parts that has something to do with frameworks. That is the initial rendering on the client and also the subsequent hot updates when the user interact with your app. So just so that we limit the scope of the talk a little bit, it's mostly just going to be about frameworks. And question, how do we measure framework performance? Obviously, the answer is benchmarks. There are so many benchmarks out there. There's the to-do MVC benchmark, because obviously every single framework implements a to-do MVC. DB Monster, this is probably just more like an FPS competition for all these new upcoming virtual DOM implementations. And this one is more comprehensive. It's called JS Framework Benchmark. The title itself doesn't really say much, but it does a lot of, it's comprehensive in the sense that it does not just the list updating, but also the initial rendering, rendering a super long list, appending to the list, removing from the list, inserting, updating, and deleting small items. So it covers a wider range of scenarios. Also covers a lot of frameworks. Shameless plug here, Vue 2.0 is right, second to the right column next to Vanilla.js, and it's the fastest in the current table. So, despite all that, a point that I really want to make is you should always take benchmarks with a grain of salt. The first reason is that it just could be plain wrong. The implementation details of all the benchmarks, they could be questionable. First thing is, many people, when they benchmark things, they just forget to turn off the development mode. So a lot of you probably know that React in development mode is much slower than in production mode. And if you benchmark React in development mode, you're going to be pretty disappointed with the numbers. Another thing people can miss is not applying framework-specific optimizations. Like when you benchmark a Negler app, a lot of people will tell you, hey, you forgot to use track by index, or you should avoid doing this, avoid doing that. And that could be just plain unintentional errors, like a wrong number in the different suites of the same benchmark. So, real story. A while ago, there was this blog post called a React Point of View that compares the rendering periodically updating a pretty big table with real-time data. One version using React and one version using Vue. So that was an interesting benchmark because that was something from a real app they're already doing, running in React. They just re-implemented in Vue, trying to test it out. And then they published a blog post saying, they were really excited, saying, hey, Vue is so much faster than React, it's so good. And React people obviously didn't want to quite just accept that, so they started looking at the benchmarks. And Vjux, who's the kind of the previous face of React, I would say. Now it's Dan. But he looked into the code, and he was like, hey, you guys forgot to turn off the development mode. You're just benchmarking React in the wrong mode. So he submitted a PR that changes it to production mode, and bam, now React is much faster than Vue. Great. So then I looked into the code again and found that there was an error in the Vue version of the benchmark where there was a set interval that was supposed to run at 1,000 milliseconds, but the Vue version was running at 100 millisecond interval. So Vue version was essentially doing 10 times much more work than the React version. So I submitted that PR again, and now we get the final correct number where Vue is slightly faster than React, but not by a significant margin. So this whole back and forth kind of tells you that like how much things could possibly go wrong when you see a benchmark for the first time. It just, you cannot take it for granted. You have to read the code, run it yourself, and also stay up to date with what PRs people send to it. And another important thing to consider when you're looking at benchmarks is that performance really scenario dependent. Because we talked about how the big grid benchmark was testing a lot of different scenarios because different updating strategies would perform wildly different when you do different things. So most benchmarks that we see out there, especially if it only tests a single thing, reflect only limited aspects of relevant performance. So there's the difference between initial loading and hot updates. Like when you render an app for the first time versus when the app is already rendered and the user clicks a button and you need to swap only part of the app, right? And also, size of the framework would play an important part in the initial loading as well. And big updates versus small updates. Are you updating just a single text field in a really huge app? Or are you replacing the entire data grid and re-rendering the whole page? Also, list juggling versus complex component trees. This is actually one of the most commonly missed aspects of all the benchmarks out there. I haven't actually seen a good enough benchmark that completely tests the second part, which is complex component trees. When we look at that previous comprehensive benchmark, it is in fact still just testing a plain list rendering plain elements. They are not components. So a lot of times what we're really looking at is the pure list juggling ability of the framework, but in reality, very few of our apps are made of only large lists. They are complex component trees with each component having its own complex DOM structures. So performance in those scenarios, there is no great benchmark for that because you would only build such complex apps in real-world apps, but how many people have the time to build the same version of that complex app in every single framework, right? It's really hard. So we talked about what could possibly make benchmarks inaccurate. And now we need to dig a bit deeper. Like, I know this is the last talk of the day. You guys are probably pretty tired, but we're going to go into some even more dense stuff. So, dirty checking. Most commonly known as the update strategy used by Angular. We have our state, we have our DOM, and the way we connect the state to the DOM is we have a lot of watchers. Every watcher corresponds to a binding in your template or a directive, and each watcher also connects to a value, an expression that it will evaluate to a value. So dirty checking essentially means whenever something changes, we don't know what actually has changed. So the only way to know is we will iterate through all the watchers and recompute their current value, compare with the old value, and if it has changed, we will then perform the corresponding DOM updates. As you can see, this is actually pretty brute force. And the perf characteristics of this strategy is the performance is bound by the cost of the watcher computations. So imagine you have a huge app with like 10,000 watchers on the page, and when you do a root scope digest, all of them have to be rerun, and it's really hard to optimize out of that. And there is a different strategy called dependency tracking, which is probably earliest seen in Knockout. How many of you have used Knockout? Great. So Vue 1.x uses a very similar strategy, but essentially we use, instead of using plain objects, well, Vue uses semi-plain objects, but the idea is your data source should be reactive. The idea is they would have a getter and a setter. Both functions would perform dependency collection and change triggering. So the system, while evaluating your templates, rendering your templates, it collects dependencies as it renders, and whenever some of the dependencies change, the system will be able to figure out which parts of the data has changed, and then the corresponding watcher and corresponding bindings then need to update. So the benefits of this system is that it's very accurate. So it's very extremely efficient for small updates. Even though if you could have like 10,000 bindings on the page, if only the dependencies of one binding has changed, only that binding needs to re-evaluate and update the DOM. So you basically short-circuit all the other ones. You don't have to do all those unnecessary computations. The cost of this system is that you need to have this dependency tracking system in place, which means you need to set up the initial model as reactive. You need to collect the dependencies when you're updating and rendering. So there will be some extra initialization and bookkeeping cost. And then Virtual DOM, which is basically pioneered by React, but there are so many different, like slightly different flavors and implementations out there. But the general idea is we would return virtual DOM trees from render functions, and when anything changes, we render again. Now we have a new tree and an old tree. We'll compare and diff them, and then we apply the patches to the actual DOM. The idea behind this is DOM is slow, JavaScript is fast, so rendering virtual DOM trees are really fast. And the perfect characteristics is it's bound by the render diff cost of the dirty subtree. So we need to realize that our virtual DOM rendering is actually not free. Like if you have a complex computation in your render function, just calling that function is not free. It still takes time. And if you have a huge virtual DOM tree structure, walking and diffing that tree is also not free. It also takes time. So it becomes critical to find ways to skip work as much as possible, which we will talk about later. But the general idea is virtual DOM diffing without any optimization is essentially dirty checking at the view structure level. And it's also bound by the render and diff costs of the tree that you're trying to diff. So when you call set state in a React application, the whole subtree from the node where you call set state needs to be walked and re-rendered and diffed. So that's the idea. And so we talked about these different strategies, and it would be interesting if we could combine some of the good characteristics of these different implementations and arrive something kind of hit a middle ground, which is what Vue 2.0 is exploring, which is combining virtual DOM with dependency tracking. So instead of having a watcher or a dependency collector for each single binding, we have a collector for each component in the tree. And when each component manages its own virtual DOM tree, and when it renders that tree, we collect dependencies. And when the dependencies change, we render that component and that component only. So this system has the benefits of being able to figure out the exact number of components to re-render when something changes. Right? There's also the same problem of small bookkeeping initializing costs, but because we reduced the amount of watchers by a large amounts, comparing to one watcher for every single binding, we now have one watcher for each component. It hits a very good balance of the extra cost and the optimization, effortless optimization that we get as a result. So it's basically auto-optimized. And talking about optimization, there is this one thing that we often overlook when we talk about performance, right? When we talk about performance, people often say, you're not, this is not the maximum performance this framework can bring about. You need to do this, that, and then you can follow all the best practices of those optimization books, and eventually you have a blazing fast app. But how much effort do you need to spend to get to that point? Right? It's different between different frameworks. This is a point recently brought up in the Elm blog post, which I would recommend everyone read about it. How much work is needed from the developer to fully optimize an app? So a very common thing that many frameworks need today as really this is almost a universal thing, is that you need to provide a hint to the framework to have a more efficient list updating. So React and most virtual DOM implementations require the key when you're rendering a a list of items, and Angular has the equivalence of track by. So since almost every framework kind of needs this, we're just gonna skip that. And the thing about React and both Angular 2 is we have this thing called should component update. We talked previously about how when you call set state on a node in a React component tree, it needs to walk and render and diff that whole subtree. So if we can imagine that a lot of the components in that subtree may actually nothing have changed. They probably don't need to update, but we still need to re-render diff them. So those are work that we can skip. And the way we skip them is using should component update. We basically just compare the previous props with the next set of props, and if they are the same, we can skip that whole subtree. But this comes at a cost, which is it's based on the assumption that the entire subtree's render output is solely determined by the props of this component. So the problem arises when you change the props that this component accepts. You need to update your should component update function implementation accordingly. And the second problem is basically none of the nested components inside this subtree can have its own external state, because the whole output of the whole subtree needs to be solely determined by the props of this root component. So now, if one of your child components depends on some external state that does not belong to this root component, we may end up in a situation where the view hasn't updated, but the state has changed. So that child component may reflect incorrect view state. Well, one solution to that is you can use immutable data everywhere and use a single state tree solution like Redux, and now all the state in your app belongs to the same place, and should component update becomes really, really straightforward. You're just doing strictly quality checks all the time. You can just use the pure render mixing or just use the pure component. But the problem is immutable data in JavaScript just is a tiny bit of awkward, isn't as smooth as in real functional languages, right? You still need to use these extra APIs to update and retrieve values. And when you are working with a third-party library that does not expect an immutable data structure, you have to do this constant serialization and deserialization between plain JavaScript and immutable data structures, which can bring a lot of friction in the development experience. Well, virtual DOM and dependency tracking, well, we talked about how it's optimized out of the box because each component tracks its own dependencies, so we don't have this problem having to implement should component updates. Or you can think of the system provides should component updates out of the box for you already implemented. And the cause is the small initializing bookkeeping cost, which in the end turns out to be relatively trivial compared to the actual cost of re-rendering. So this is the direction I'm exploring in Vue 2.0. Obviously, I'm biased, so there might be other problems I haven't seen, but I'd be happy if people provide feedback on what they think this system works. And a really important thing I want to mention is Elm, because Elm is doing some really great stuff in that it's a language that basically guarantees the purity and immutability in your data structure and your functions. And what these guarantees provide is that we can make skipping work really, really simple, because when you render a subtree in Elm, you can turn a whole subtree change a whole subtree, make it optimized by wrapping it inside a function called lazy. And this lazy function will accept a number of arguments, essentially the equivalent of props in React components. And this lazy function will just compare these arguments to see if they are equivalent. And because everything in Elm is immutable, right, it's really simple. So also very efficient. And also because this pure function guarantee, there's no problem. The problem should component update faces where you may have an impure component down the tree. And finally, you don't have to actually use components to get this benefit. You can wrap arbitrary subtrees inside the lazy function. So Elm really reaches a really good point where you don't really need to do a lot of work to optimize your app, but well, it's a pros and a cons at the same time. You get to use Elm if you love it. You have to use Elm, and you have to learn it because it's a whole different language. It's not JavaScript. But that's really up to you. So another thing a lot of people mentioned about is web workers. So we know that today modern JavaScript frameworks are getting heavier and heavier. And so imagine if you have to wait like 100 milliseconds before anything happens. And when we think about virtual DOM, right, a lot of work, the proposition was that the real DOM was slow and JavaScript is fast. So we do most of the work in JavaScript and only apply the minimal amount of DOM manipulations. And turns out, when the app is huge, JavaScript is expensive too. And we spend a lot of time just doing expensive JavaScript computations, number crunching, walking trees, calculating diffs, and all that. So why don't we move them off the main thread, right? Like if we have multi-threaded JavaScript, if we do all that work off the main thread, we would have a more responsive main thread. A common problem people talk about is when you click a button and if you have something really expensive going on, the whole page just freezes and you can do nothing until it finishes computing, and then the page becomes responsive again. If all this work is done off the worker thread, then your page still remains, at least you can scroll during that period of time. And when the computation finishes, the worker thread sends back the actual DOM updates to update the page. Right? So this results in more responsive interactions in theory. But in reality, the gain is pretty marginal. After testing it with the existing implementations, there is a React worker implementation, and there's a worker implementation in Angular. The intrinsic problem is, although the work is being offloaded to the thread, you're still doing the same amount of work. So the CPU isn't magically faster. The user still has to wait the same amount of time before anything actually meaningful happens. Although they can scroll while they're waiting, but if your app is so slow that the user can scroll after they click a button before anything happens, it's probably wrong in the first place. And then there's this increased development complexity. When you run your application in a different thread, the whole thing just becomes a lot more complex. Now you have an environment, a sandbox environment that has no access to the DOM. So you have everything, all the code that you run inside the worker thread cannot touch the DOM. It has to be purely decoupled from the DOM. They have to be pure computations. And then you need to have this rendering layer running in the main thread that receive these DOM updates from the thread and then apply those updates. And you need to manage the protocol between the communication protocol between the two and make sure everything is well orchestrated. So it just adds a lot of development complexity to the thing, and which is probably the reason why we haven't really seen web worker-based render architecture widely used in real apps. But people are still exploring, so maybe one day we'll have a really smooth experience. Then that would be a great idea that everyone should use this. So we talked a lot about these dense stuff, right? Takeaways. And takeaways similar to all the talks that compare between things. We don't have a winner because the question at hand is complex by nature, right? The first thing is take benchmarks with a grain of salt. Read the code and run it yourself. Don't just look at the numbers and then run around yelling, this framework is the fastest, right? It may very well not be the case if you run a different benchmark. Have a big picture understanding of the merits of different render mechanisms. So we went pretty fast in that section, but the idea is different rendering strategies have their own unique characteristics under different scenarios. So some rendering strategies are naturally faster at initial rendering. Some of them are good at handling small, very frequent updates. Some of them are really good at just re-rendering the whole thing. It is It is probably pretty hard if you want to like dig deep and understand the ins and outs of every single framework out there, but it's helpful to have a really high level idea of what the characteristics of each strategy generally have. So when you see a virtual DOM implementation, you kind of instinctively know what it entails. And more importantly, you need to identify the perf priorities of your app. Right? The web is very versatile. We build all different kinds of apps. Some apps really demand fast initial page loading because like 1 millisecond difference can cost your company money. But some apps, right, like dashboards or long-running applications, we don't really care that much about initial loading. We care about memory usage over the long run. We care about efficient updates, constant real-time updates flooding in and keeps chunking. And there are also apps where just requires FPS. Maybe you're building a real-time visualization that just need to run at 60 FPS per second. Then different implementations would have different optimization requirements for these different scenarios. So important to look at the app that you're trying to build and identify what is the most important perf characteristics that it requires. And combined with the previous knowledge of different rendering mechanism, you can likely pick one that is more likely to, to handle the scenario better. And then it's time to build. But before we actually dive into it, I would suggest building a number of prototypes with a short list of things that you want to try, and really bench them to get the real numbers. If you don't do that, imagine if you realize 3 months down the road, the app just becoming too slow, and now you need to do a full rewrite. You will probably thank yourself if you spent that first week just exploring different strategies and possible solutions. So that's actually all I have. I think I did run it pretty short, but that's all I have. Thank you.